Welcome to the fourth day of the WavyTropics Workshop. And today we will talk about mixed Rossby-Gravity waves. And as usual, we will start with a weather briefing given by our forecaster, Thierry Lefort.
Hello, everyone. Where are the people online? Where are they from online? Are the people from Papua New Guinea, maybe? Or because we are going to speak about the Western Pacific, especially with the mixed Rossby-Gravity. Okay, share screen. All right. I'm starting with the view that a forecaster could have on his workstation, which is a comparison of 4 global models in the streamlines and so 925 hectopascal streamlines. We also have the mean sea level pressure, which is not so visible. And the colors are the rain accumulated in 24 hours in each model. So each model rain. So the red, purple is the max, or even green sometimes. So this is a prediction for Saturday 0, which is like 48 hours prediction. So an important task of the forecaster is to make the best use of the numerical prediction models. So as we say yesterday, and it's in the discussions, it's important to not to use only one model, because if this model is wrong, then we would follow a wrong solution. So there are different possibilities. The first possibility is what we call the poor man's ensemble, which is use global deterministic models. So here we have top left UK MO, UK model. Top right is ECMWF. Bottom right is the access, the BOM model access, and bottom left is JFS. We will not speak too long about it, but of course the forecasters, they must know the differences between the models. Some models have a grid space which is more precise than others. So if you compare the accumulation of rain, the maximum of rain that the model is building, of course, the smoother the model, the lower the maximum amount. I mean, a fine mesh model is able to produce 300, 400, 500 millimeters in a day, but a smooth model, a large grid space model cannot. So you cannot compare exactly the absolute values because each model has not the same grid space. ECMWF is 9 kilometers, for example. Well, they are maybe a bit similar, but not exactly. So that's important. Okay, and if we look at, so the game is to find, is there a significant difference? Do the model agree? Is there an agreement of the models? So that's about deterministic model. Another solution would be to use an ensemble model like the European ensemble or the American ensemble or the UK ensemble. When you use ensemble, unfortunately, you still find that the spread of each ensemble is a bit, I mean, if you find a difference between, well, that's what we have in Europe. If you find a difference between 2 deterministic models, you will find the difference in the ensemble mean, for example, too. So very often, the ensemble are still too much centered over the deterministic, which means that actually the uncertainty is the sum of each ensemble, which is, so it's a kind of using multi-ensemble. So for the short range, we are here on deterministic. And what I want to show you is the GFS solution. If I zoom in near Malaysia, and if I remove the rain because we don't see anything, so I'm removing the rain, you can see that the solution presented by the GFS is very different from the solutions from the other models. So the GFS produces for Saturday morning a deep tropical depression, and even if you look at the strength of the wind, you've got 40 knots sustained winds and 1998 hectopascal, which is a tropical storm. So the first job of the forecaster is to decide if he trusts or not this kind of solution. Probability, maybe according to the climatology and to the fact that the other models don't show that, is that the GFS is maybe a bit it's isolated, we would say, compared to the other models. So the first thing for the forecaster would be to look back to the previous runs, and usually the other runs would not show the same or would show not as deep. So that's just to emphasize the role of the forecaster, because if you want to plug some digital forecast based on GFS, then you would have a tropical storm and strong winds and so on. So if there is no pilot on the plane, you could send some wrong or information. Okay, that was just a remark for the forecasters. Now, I would like to show some examples of what we've seen these last days. So I will show you some archived charts. This is actually on Synergy also, the workstation. These are archived. So what do you recognize on these low-level streamlines and wind and mean sea level? Low-level streamlines, for example, 850 streamlines. What do you recognize as conceptual model? You can answer in the room and on the chat. What equatorial wave do you recognize? That's the question. Yes, equatorial Rossby, yeah, thank you. So you recognize the westerly burst, equatorial westerly burst, and symmetric cyclonic circulations. A mixed Rossby-Gravity, well, our scientist will present the conceptual model. A mixed Rossby-Gravity, you will have, I will show some examples later, you would have the cyclonic, well, the clockwise or anti-clockwise circulation just centered over the equator. You would not have westerly burst over the equator. We will see the conceptual model later. Oops, that's not this one. This is also a kind of screenshot over the Indian Ocean with the rain and surface wind and mean sea level pressure. It's a sequence from top left to bottom right, a sequence which is the real case, and you can remember what the Adrian Matthews showed us on the theory. You've got some westerly burst and some rain at first, and then you've got some almost symmetrical vortices. This is what it looks like on a model field on a workstation for the forecaster. But then again, a sequence of operational charts, so traditional charts. Okay, this is a traditional total flow. So on bottom left, it's the 850, bottom right, 700, top left, 600, top right, 500. And it's the humidity field in purple and the wet bulb potential temperature in colors in this shading here. So the yellow, the orange is the moist air mass. This is 850. So compared to the theoretical conceptual model, you can see that, well, here that we don't have a very nice equatorial westerly burst. There is a bit of a cross equatorial flow. At 600 and 700, it's a bit more zonal. So it's not always exactly the theoretical conceptual model. And then if we continue the sequence day by day, for example, this is what it looks like. You have a strong 35 knots, a strong westerly burst. This is in September. It's a September case. And still continuing a very strong westerly burst with a symmetric vorticity centers. Like this. So an equatorial wave really looks like this kind of I would say a bit of a jellyfish pattern. I don't know if you recognize a jellyfish, but I see a jellyfish. And sometimes we have, a four-wheel, what I call a four-wheel equatorial Rossby. We've got two different symmetrical vortices. We can have four tropical systems at the same time. When we can have two consecutive equatorial Rossby, or it's all this is included usually in a large MGO envelope. So in the most active MGO envelope, we sometimes meet this kind of patterns with four different tropical systems or tropical depressions. Well, on satellite pictures, this is what it can look like. This is the Indian Ocean. We can have, this is the kind of, you see what Adrian showed about a dry equator, and the moisture is symmetric, but it's dry at the equator. That's mostly at the end of the process. That's more at the beginning, and that's down is more at the end. Okay, and now a nice streamlined analysis produced by Hawaii Weather Center, NOAA Hawaii Weather Center. I like this kind of charts. It's the surface streamlines. So what do you recognize? Too easy. You recognize the symmetrical vortices, and westerly, we don't see the strength, but it's an equatorial Rossby again. So
there's a question. May I know which satellite it is?
Sorry?
May I know which satellite it is?
This must be Meteosat Indian Ocean. I guess the end of the image is there. So it's Meteosat, which is a bit east of the Greenwich Meridian. But in the history, they have moved a lot, the Meteosat. So this was a few years ago. So I don't remember which number it is for Meteosat, but it's the Meteosat a bit Indian Ocean, where it used to be. So now, this is French language, where you have the WB, westerly wind burst. So this is what a Kelvin wave, a big Kelvin wave looks like over, if I zoom in, near Sumatra. This is what Japanese school, I would say, what Japanese scientists call a supercluster. It's a very big area, a very big cluster of cumulonimbus, which, when we look at ASCAT winds, I really recommend the forecasters to use ASCAT winds to check the surface observations. And you can see the leading edge of the westerly burst, 25 knots. And ahead of it, it's weak winds. So you've got a strong convergence just ahead of the wind of the strong winds. And then the next ASCAT was is this image. So you can see Padang and the strong westerly burst reaching the coast of Sumatra, and then progressing, deflected by the mountains of Sumatra. Not yet, but that's the beginning of the deflection of the mountain. And you can see the pre-existing wind, a very weak wind ahead of it. So this is a kind of what I call a mega squall line. It's really a very big squall line. And that's maybe another one. So that was in January 2020, 29th of January in Padang. No, sorry, Central Tapanuli, North Sumatra. And Angin Kensang di Padang, strong wind also. The strong wind is brought by the gust from this super squall line. This is in Synergy website, a Synergy tool. This is the 925 hectopascal wind, humidity, and the blue is the dry dew point. I think. No, it's the humidity, sorry. No, it's the strength, sorry. It's isotax, it's the strength of the wind, sorry. It's 36 knots, 40 knots, 36 knots. So you can see the size of what looks like a squall line. All right. Could you hear me when I was talking about the Kelvin wave? By here, yes, but well, okay. No?
Can you hear me? I can just pass my mic to Thierry. Yes, okay. Then
Okay, I was showing an example of a westerly burst and a Kelvin wave over Sumatra, which looks like what the Japanese scientists call a supercluster. It's a mega squall line, and this is through the Ascat winds, showing strong westerlies reaching Sumatra, and and this is another case where you can clearly see on satellite picture and with Ascat winds showing the strong westerlies behind the leading edge of the squall line. And this is the cross section. This is the wind with the isotax, the strength of the wind isolines in Synergy workstation. And then, so it's like 36, and max is like 36, 38 knots. And then I make a cross section across Padang, and this is the cross section with the very deep westerly flow and the blocking by the mountains of Sumatra. And the result, the impact on Sumatra. Also strong winds reported. When as a regional forecaster you have some reports of strong winds, it's very important to understand if it's usually it's a convective gust, it's convective gust winds, wind gust, a local, very local convective, or is it a synoptic? All the region had strong winds, so it's important to distinguish what kind of strong winds. Okay, so I'm leaving this. So now I'm going to internet. Yes, I wanted to come back to the question yesterday. Do we expect extreme weather because of the MGO and the Kelvin wave? Just to add a comment, a comment about this is that when you use Hofmöller are very interesting because they show the propagative signal, but they also show the past, well, a few weeks in the past, and it helps you to understand if what is expected is big or not big. For example, in the past, recently in the Western Hemisphere, Western Pacific, there was a very, you see the colors of the anomaly of VP200, it's white. It means it was a very big anomaly. If you look at, so what is forecast? Of course, when it is forecast, there is some spread of the ensemble. It's not an analysis, so you will never expect the same dark colors because there is a spread. But a first indication is that we said that the MGO would cancel the subsidence of IOD and El Nino, but there is no dark green. It's a bit of green, that's all. So it's a first, it seems very basic, but it's very efficient. It's a first indication that at a large scale, we are not dealing with a local extreme. We are dealing with a synoptic extreme pattern for several regions. We are dealing with a scale of the MGO and not, I mean, for example, in Makassar event, it was only Makassar who had floods, not all Sulawesi, not all Indonesia. So I'm not talking about a case like Makassar, but I mean, Makassar was included into an MGO. But at a larger scale, there is no signal of something big. If you look at 850 wind, you've got also in the past you had this quite a strong westerly burst over the West Pacific, and here now you have quite a significant westerly burst over Africa. But you don't have significant westerly burst over Indonesia, for example, which would mean maybe the onset on the monsoon, for example. So it was just a very basic rule of thumb that only with looking at the darkness of the colors, it gives you an indication of the fact that it's not, well, it's unlikely that there is a big something, but at the scale which is a bit larger than one city. It's a larger scale. Okay. Okay. Now I want to show some some archives again, which are the traditional chart for the forecasters. Alors, j'arrive pas à... Yeah, because I need my... je peux faire? I put it here.
We will check if the other mic is working.
One, two, three.
Can you confirm?
Does it work? Because it's much easier for me to zoom in.
Yes.
Okay. So I want, before the scientists explain what is a mixed Rossby-Gravity, I can show you some examples. So it can be in one, okay, scientists first and examples behind, but it will be examples first. So this is an example. I will be fast over the Atlantic Ocean. This is a total wind, a total surface wind. You can see a cyclonic circulation west of Africa with some clouds. And on Philippe Perrier product, there was a very clear, a very big MRG signal here across the Atlantic, which is not above the equator, which is north, which is more above the well, the active ITCZ. So, and then 2 days later, the vorticity has moved west, and west of Africa, there was a lot of anticyclonic vorticity. And you can find it here. You still find you can find the anticyclonic vorticity of the MRG. So this was a very big event. So I'm moving now to the Pacific Ocean. Yeah, I'm moving to the Pacific Ocean. So over the Pacific Ocean, so over the West Pacific Ocean, so it's very useful for Papua New Guinea, for the Solomon Islands. They will be very much impacted by mixed Rossby-Gravity and all the islands which are across the equator. You've got, sometimes you see some cross-equatorial flow which moves west, which is not a monsoonal flow, which is a very temporary cross-equatorial flow. So northerly, then southerly, and when you follow these patterns, you can see right here, you have some very nice vortices. Well, this is a total flow. So it's not only you have all kinds of waves inside. So what we are looking at in, for example, Carl Schreck products will be the meridional wind, the V850. So the V850 is very useful for the mixed Rossby-Gravity because mixed Rossby-Gravity, they travel above the equator and they provide some northerly and southerly components. So we will follow this kind of wave trains. Usually, very often they are not only one cyclonic circulation, but it's a wave train. And this is the, okay, that's the illustration. So on the right, it's Carl Schreck's website with the V component. So orange is southerly component, southerly anomaly, and blue is northerly anomaly. And on the forecasters chart, on the left, you can see a nice cyclonic circulation across the equator. So we will have a discussion with the scientist. Is it cyclonic? Is it anticyclonic? Because it's across the equator, so it's according to if you are north or south, it's not the same. And then at the same location, you see east of Vanuatu, east of the Solomon Islands, sorry, the mixed Rossby-Gravity will provide a northerly surge, which will help increase the vorticity east of the Solomon. And then again, you have some southerly, so it's a wave train. Okay, I close this, and then I'm going to the internet. Alors. Yeah. I want to show today's situation is not it's not very good it's not very clear. So I decided to check last October, a few weeks ago, there was a very intense tropical cyclone in Vanuatu that formed on the 21st, well, it was named on the 22nd of October by Fiji. Sorry. So I'm going on Philippe website, Philippe Perrier's website, Météo France website. I'm going on the wind vector, 700, Pacific Ocean, and in October around the 19th of October, for example. So that's the situation a bit before the real deepening, which is important. First, the first information, if you look at low frequency, the low frequency was already providing some vorticity because you have a westerly anomaly due to El Nino over the equator, and south of it there was easterly anomalies which were maybe related to the southern hemisphere annular mode, I don't know, but so it makes vorticity. You understand? There is vorticity above the Solomon Islands. So the low frequency is already favorable, brings some favorable ingredient. The MJO, there was a westerly, the MJO was westerly with a bit of vorticity also, but mostly for Vanuatu. And now let's focus. Okay, there was a nice Rossby wave, a great. That's the westerly burst I show you on the 850 wind. So that was the very strong equatorial Rossby with almost symmetric cyclonic vorticities on both sides. Okay, so you see that the equatorial Rossby is providing some vorticity for the Solomon Island and Vanuatu, as well for the Northern Hemisphere. The Northern Hemisphere is what followed by the Japanese Met Agency and what did not become a tropical storm. It was a tropical depression. So you've got the low frequency, the equatorial Rossby is very favorable, and then in the MRG, I will animate so that you can see the wave train. You can see the wave train. an MRG is always as a wave train, is not isolated, is a wave train. It's very common in the West Pacific and also over the Indian Ocean. Not so common over the maritime continent, Indonesia, but still, it is you can find some of them. So what we are, as a forecaster, what I see for the importance for the wind field, for the wind field, because then it will bring also some moisture. But in a wind field, when you superimpose the vorticity from the equatorial Rossby and you add a northerly component, you add a northerly cross-equatorial component, then you help to close, I would say, to close the isobars. You help to close the cyclonic circulation, which if you only have equatorial Rossby, you would have a westerly only, but it helps to, well, to focus the vorticity at the same location. So if we, to finish, if we look at stream function and wind at 700, yes, sometimes 700 is clearer than 850. So let's look at the wave train here. You have a nice wave train. So you understand that when you add the red, which is the cyclonic vorticity from the equatorial Rossby, you've got the orange, which is the cyclonic vorticity of the low frequency. And then you add, when you add the cyclonic vorticity and the northerly flow of the MRG, and then you have a max of total vorticity. And you see that the total anomaly is very similar to the sum of the waves, which means that for this case, the waves are explaining a large part of the vorticity, which was the environment of the future tropical cyclone in Australia, tropical cyclone. So I'm not. So this is just as we saw the environment, and then the physical processes for why did Lola deepen as a category 5? I don't know. It's not the question of. It's just a question of the start of the process, and then there are more complex, rapidly intensifying processes, etc., which are not dealt today. This is just the launching of the process of deepening. Okay, that's all. Thank you. Time for questions.
As always, thank you very much for such a nice weather briefing. So we will be taking questions now. There's one question in the chat so far.
So we have observed such cases over the Indian Ocean where cyclonic circulation is neglected over the equator, where half circulation is over positive north, and these evolve into cyclones. Maybe these are MRG, but very short-lived, which evolved due to interaction with MGO. Yes, the MRG are very short-lived. They are not short-lived, but they move west rapidly, so that the cross-equatorial flow brings some vorticity and convergence according to the theory of where is the convergence. One day at a place and the second day at another place. So it's usually not enough to produce a long-lasting cyclonic circulation. Very often the equatorial Rossby is something which is the MRG is something which is added to the equatorial Rossby. Not always, but often. Yes, it's like a modulation of the equatorial Rossby, and one or 2 days it adds the vorticity, and the next 1 or 2 days it removes some vorticity.
more questions? We still have at least 5 minutes.
Anyway, we will have the presentation about them, so you will have more questions.
So
the same remnant of what the GFS is doing in the South China Sea, you mean? Yes, yes. That's the cyclonic circulation. In the previous days, the GFS was deepening, but much later over the Indian Ocean, and the last run is deepening very fast. But then it weakens the low when crossing Malaysia. But it's very rare to see especially even the GFS deepen so much just in 48 hours range. It's really the convective process of the heavy rain which makes something with the heat release, and we know it seems that the GFS is a bit hyperactive, but usually it's mostly in the medium range. But what we show here is only 48 hours, which is very rare.
all right, then we will make a break now, and we will continue 3:15. So in a little bit more than 15 minutes. Welcome again at the continuation of the third day of the WavyTropics Workshop. And now we will have a science talk given by Dr. Ida Pramuwardani from BMKG. She's here with us in BMKG Jakarta. Ida, the floor is yours.
Thank you, Beta. I'll share my presentation. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon from Indonesia. So today I would like to share about the mixed Rossby-Gravity wave because a couple days ago you already learned about the, maybe not learn but discuss about the other equatorial wave like Rossby and Kelvin. So today is mixed Rossby-Gravity wave turn. So my name is Ida Pramuwardani and people usually call me Ida. I was a forecaster, but now I'm handling the production in BMKG in weather forecast. So at the first part, I will share about the information about the mixed Rossby-Gravity wave in theoretical, and in the last part, I will share about the equatorial mixed Rossby-Gravity wave influence in Indonesia, in maritime continent, but especially in Indonesia. So the mixed Rossby-Gravity wave or MRG wave is a part of equatorial wave that play a significant role in the tropical regions. I think I need to show the sorry. And the convectively coupled equatorial wave or CCEW is an equatorial wave that also coupled with convective, and it is generated by diabatic heating due to organized tropical large-scale convective heating in the equatorial belt, especially in the region between 20 degrees north until 20 degrees south. And it is also generated in the troposphere by large-scale convective system in the equator. And the MRG wave characteristic, it is based on a paper from Holton in 2004, have a period about 4 until 5 days. It is shorter than equatorial Rossby, of course, and it's propagated westward like equatorial Rossby, but it's faster than equatorial Rossby. And it has a vertical wavelength about 4 until 8 kilometers. And from the paper from Setiawan in 2010 and also Lubis and Jacobi in 2015, MRG have influence in the tropical region, especially for the tropospheric circulation, and also it influenced the precipitation characteristic in the tropical region. So this is a structure of, this is a structure of MRG based on space-time spectrum. In the left panel, we can see MRG is an antisymmetric wave. We see here in this line, it is a dispersion of MRG. I think you already seen it a couple days ago. Maybe if I'm not forgotten in the Kelvin, but this is for equatorial for MRG. We see here that there are a significant signal for MRG in the equatorial wave, the equatorial region. And this image is obtained by the method from Wheeler and Kiladis, space-time for calculation and plotting. The data used were from INCAP reanalysis from 2001 until 2005 on a grid 2.5 degree grid with 4 times per day. This is for the left panel. And this information is a zonal wave number for horizontal, and for vertical it is frequency. So if we see the middle figure, we see that this is the dispersion diagram for each wave, for each equatorial wave. We see Kelvin have a straight line, and equatorial Rossby it is westward, and mixed Rossby-Gravity wave it is also westward. And we also have a high frequency for inertia gravity. So for the eastward line for mode 0 or N0, this is for inertia gravity eastward. So we have to take a look that the MRG is in this region, in the black line, westward black line region. So if zonal wave number and frequency spectra from 15 years stream dataset, this is for the RAC one. So we, in our research, we try to split the zonal wave number frequency spectrum into two periods. The upper panel is for boreal winter, and the lower panel is for boreal summer. So this cover the region, this all the globe region. We see here that during boreal winter and boreal summer shows a significant signal for MRG. And as I said before, MRG is antisymmetric wave. And this is the structure of MRG wave, and it is, I get it from the Sandro, Lubis, and Sonistia paper. This picture simulates a geopotential field and horizontal wind perturbation corresponding to Yanai wave for mode N0 with zonal wave number 0.5, 1, and also 1.5. We see here in the left panel above is for wave number 0.5, and the middle is for wave number 1, and in the right panel is for wave number 1.5. We can see here that the increasing of wave number can result in increasing number of wave pattern here. And we see here, we can see the antisymmetric pattern where it also shows the perturbation region. We see here the red one with the blue one. We see the opposite condition or opposite amplitude for the wave here show us or indicate antisymmetric condition. And this is the MRG wave propagation related to the convective condition. In the right panel, we see that this is the structure of mixed Rossby-Gravity wave. We see here, this is from Gelades et al. In 2015. We see here that geopotential low in the northern part and geopotential high in the southern part. And it's has also the convergence or the perturbation here, high perturbation here, and the surprise here, the divergence in the southern. So it is it is indicate that this wave is antisymmetric, even if this wave is coupled with the convective condition. So if we see a geographical distribution of the or geographical propagation of mixed Rossby-Gravity wave from the Lubis and Jacobi paper in 2014, we can see that here the wave is propagate westward. There are significant surprise of the rainfall anomaly in the northern part, and increase of significant precipitation anomaly in the southern part. And sorry. How can I show the True, no, no, bro, but how can I show the red dot? The red dot? I can find it. Cannot find it.
Wait a second, we are searching for an option to draw something on the screen.
No, 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 I don't think that's okay. I just continue it. Sorry. And we see that here.
Again, we can see your mouse, but it's also white.
Yes, I try to
yeah.
find it, but I cannot find it. Di mana cara mouse-nya? Buka, lihat mouse-nya itu di mana ya?
Terus kalau buat anotasi biasanya
Nggak ada ini.
ini Bu, ini bukan kalau mau nulis gini.
Bukan sih, cuma mau lihat aja. Ini, bukan mau nulis, tapi mau lihat.
Lihat apa?
Mau lihat itu loh, yang titik-titik merah itu loh.
Oh, kayak pointer gitu ya?
Pointer.
Kayaknya sih ada anotasi ini. Ini mungkin.
Ini bukan?
Code. Ini spot.
Okay. Sorry to take a long. So, MRG wave propagation is propagated from composite filter MRG wave from trim data like regression. It is based on Lubis and Jacobi paper, and base point denoted by the star point here. And it is located in the West North Pacific, and we see also obviously that the wave is propagated westward. And this is the variability information of the MRG wave during boreal summer and winter. It has also come from Lubis and Jacobi paper in 2014. We can see here that during a boreal winter, we can see that the perturbation or the variance is significant split into two hemispheres in the northern and also southern part hemisphere in the area of Pacific Ocean, but in maritime continent it is more to the south. And for Indonesia, it influence or it has a significant variance in Java and also in Bali, Nusa Tenggara. And during the boreal summer, we see here that the wave is going more to northward. We see that the significant variance of a mixed Rossby-Gravity wave is in the central Pacific, but in the northern hemisphere. And the total precipitation variance during boreal winter, November to April, in the left panel shows less precipitation over Indonesia region except central Java and Nusa Tenggara. And boreal summer in the right panel shows absent precipitation in the region in Indonesia, but with minimum intensity in the North Pacific Ocean. However, if we see a whole of maritime continent, we still can see during boreal summer, we can see that the area of Philippines and then Cambodia, Vietnam, Myanmar, and also in Thailand, we can see a significant hike variance, and also in the Central America and also western part of Africa. And from Takasuka and Sato 2020, it also reveals that MRG wave have a contribution to the MGO initiation. So MRG with tropical depression circulation, it is induced convective triggering that also initiate the MGO and in the region of Indian Ocean. And it's turned out that MRG with TD type circulation or MRG TDs are possible drivers of convective initiation and propagation of the Mendin-Julian oscillation, and it's occur in the Indian Ocean. And the finding challenge existing MGO theory, suggesting that MRG TDs plays a crucial role in MGO initiation and propagation, emphasizing the importance of high-frequency dynamic in triggering the convection. And this is also, as I said before, I also would like to share the result of my research previously. We used data with 15-year long of the TRIM data for filtering the mixed Rossby-Gravity, and also using to plotting the precipitation anomaly. And we also use a 30-year long data for 850 hectopascal zonal winds from era interim reanalysis, because it's already a long time ago. So I still use era interim reanalysis for identifying the extreme West North Pacific and Australian monsoon. And we also using 12-hourly multi-level wind from BMKG sounding data to identify the multi-level wind, to investigating the local atmospheric dynamic. And for methodology, we also examine the extreme West North Pacific and Australian monsoon days. We use method from Wang and Fan, and we also use the method from Yin et al. And it turned out that for extreme West North Pacific monsoon occur in Indonesian region during December, January, and February. And for the extreme Australian monsoon, it's occur during July, Augustus, and September. So the West North Pacific, or it is ASEAN monsoon, occur have a influence during December, January, and February. But for Australian monsoon, it is during July, Augustus, and September. And for filtering the mixed Rossby-Gravity wave, use Wheeler-Kelladis method and using frequency and wave number domain using dispersion diagram. And for mixed Rossby-Gravity wave active day, we use the method from Zhao et al. In 2013. We identify the peaks of expansion coefficient normalized unit above its standard deviation to determine the active days of MRG wave. And MRG wave propagation stage, we also using two empirical orthogonal function using lag regression method, and we comparing those two AOF1 and AOF2, and we find out that the AOF1 is better, give the best pattern for MRG wave. And for MRG wave propagation days, we match with the extreme West North Pacific and also Australian monsoon days. And we also investigate the precipitation anomaly to see the local precipitation characteristic, and we also investigate the multi-level wind to find out the local atmospheric dynamic influenced by the MRG wave. And this is the result that MRG variability during ASEAN and Australian monsoon in Indonesia. I'm sorry, my research is only focused in Indonesia, but I hope that it can give you maybe a good example to identify the MRG characteristic in other region. So the left panel is for the variation of MRG during December, January, and February, or during a boreal winter, and the right panel is the MRG variability during Australian monsoon or during a boreal summer. Sorry. It's show us that MRG variability spread evenly in the tropic, north and south during ASEAN monsoon in December, January, February, even though the amplitude or the magnitude of the perturbation is not too significant compared to during the boreal summer, because we see here that during boreal summer we have a more significant perturbation in the northern part of the Papua Island. And mixed Rossby-Gravity variability higher over the northern hemisphere during Australian monsoon or during July, August, and September. And we can see here during boreal summer, we see a quite clear condition in the southern Indonesia region. And again, I concentrate in the Indonesia region. So this is the evolution of emerging wave in Indonesia. We see the two left panel is for evolution for during the Australian monsoon, ASEAN monsoon, I mean, and the two right panel is for evolution during the Australian monsoon, big Australian monsoon. We can see here during the boreal winter, the Indonesia region, especially in the southern part of Sumatra, Java, Bali, have a significant influence of emerging wave during day -1 to day day 0 because I'm using a log regression, and then it also significant for the extreme West North Pacific because I also divide the period into the active in the right one and the extreme one in the right one. So we can see also during the active condition, the amplitude of the emerging wave is more significant than during the active one. So active one mean all the period during the December, January, and February. And this is based on empirical orthogonal function 1. And we also can see here that during the boreal summer, we can see here that the wave is tend to locate in the northern part of northern hemisphere, far away from Indonesian region. We can see that maybe the Philippines region is influenced by mixed Rossby-Gravity wave during the boreal summer. And this is the rainfall duration related to MGO and convectively equatorial wave, including MRG, because our research is not only in MRG only actually, but also we also investigate the other wave like Kelvin, Rossby, equatorial Rossby, mixed Rossby-Gravity, and also inertia gravity with mode 1. And we see in the left table is the average of convectively coupled equatorial wave and MGO significant perturbation events in Indonesia region with the perturbation more than 1 millimeter per day for each coordinate grid point. So in one coordinate, it can mean that in one location in Indonesia. And the right table is the average of CCEW and MGO propagation duration over the region of Indonesia. It can mean that the propagation time from the western part of Indonesia until the eastern part of Indonesia, vice versa. So we can see here from the left table, we can see that in one location, the MGO takes 15 days perturbation or 15 days active condition in one coordinate or one location. Kelvin 2 days, equatorial Rossby 6 days. It's quite longer than other equatorial wave period. And for MRG, it similar with Kelvin 2 days. So MRG took 2 days in one location in Indonesia. And the right panel, it also shows that during the duration of propagation, I'm sorry, it is still in Bahasa, but the duration of propagation from the eastern part of Indonesia to western part of Indonesia. For MGO, it's take 22 days, Kelvin 2 until 3 days, and equatorial Rossby 7 until 10 days because it's slower than any other CCEW wave. And MRG took 2 days, and the last one, inertia gravity, 1 day. This is the MRG propagation from stream data. So based on the propagation or evolution we see from the previous slide, we make a composite here, and we can see this is also, if I'm not forgotten, still from 15 years composite data set from TRIM data. It can show us that during boreal winter here, it can give indication that Indonesian region also influenced by mixed Rossby-Gravity wave, especially in Kalimantan region. I think it also covering the Malaysia region, and also in Sumatra and also in Java, especially during day zero. I also using a like recreation method. During like day zero, we see here that the condition is quite significant in the Borneo or in the Kalimantan region, and it's decrease in the next day. But during the boreal summer, we see here that the wave is, or the perturbation is concentrated in the northern part of Indonesia, like in the northern part of Papua Islands, and it's go to the west region, and it give an impact in the Philippines in day one. And MRG propagates westward from day -1 to day -1 to day +1, indicating that the wave prominently influenced the east central part of Indonesia archipelago, and MRG perturbation tends to be located northward during the Australian monsoon phase or boreal summer, and located more southward during the ASEAN monsoon phase. And the impact of MRG wave to the rainfall anomaly in Indonesia, we can see here, it's the table is complicated, I think, but I try to simplify it. So based on the investigation of the influence of the MRG wave in Indonesia, we can see that the mixed Rossby-Gravity still influence the rainfall anomaly in Indonesia about 50%. More than 50%. We see here the active is whole December, January, and February, if I'm not forgotten, active phase. And this is extreme. I quite forget because it's have been a long time ago. But in general, the mixed Rossby-Gravity wave, it's influenced the positive anomaly and also negative anomaly in Indonesian region here for more than approximately 50%. But for extreme condition, it can increase the anomaly more than 70%, but it cannot significantly suppress the anomaly of the precipitation. It means that the monsoon still plays significant role rather than the mixed Rossby-Gravity wave during the extreme monsoon condition. And we also identify the precipitation anomaly during active mixed Rossby-Gravity. We take the example for several stations in Indonesia, several locations like Medan, Padang, Tangerang, Surabaya, Makassar, Manado, and also Kupang. And to make it fast, so I make it simple. So the positive anomaly occurred in Makassar during the West North Pacific monsoon or ASEAN monsoon condition, or during the boreal winter, but it also increased or adding the precipitation during the boreal summer. So it can conclude by less local precipitation anomaly for MRG wave and for both the West North Pacific or Australian monsoon phase or boreal winter and boreal summer compared with Kelvin and Equator Rossby. So it is have less significant influence compared with Kelvin and also equatorial Rossby. And a big positive anomaly still occur in Makassar at day +1 during December, January, and February, and in Manado, here in Manado, at day 0 during the boreal summer, coincides with the positive mixed Rossby-Gravity wave perturbation, still indicate that the local MRG relationship, even though with a lesser anomaly rate.
I'm sorry, there's a question in the chat regarding this particular slide. So if you could tell more about the methods, how did you do this analysis?
The previous slide?
Yeah.
Yeah. This one? Yeah. Okay. So I think I have to read it one by one. So active means active monsoon. If you have, okay. I can answer it detail. You can contact me personally if you want to know more about this, because it's quite a long time ago, so maybe I can read it to you. So the active means active monsoon. It is from December, January, February, and also July, August, and September. Extreme means active monsoon above its climatology condition. So we also determine the climatology condition. So the extreme mean the active monsoon. We see which is the day with the above climatology index. The index, yes, monsoon index. Yes. The positive means rainfall anomaly increased during active and extreme CCEW, and negative means rainfall anomaly decreased during active and extreme CCEW. And significance value means the perturbation of more than 1 millimeter per day, so it is significant. This is all the positive perturbation, and significant is the most significant. It is come from the perturbation more than 1 millimeter per day, and overall CCEW drives the weather condition in Indonesia by more than 50%. And the rainfall anomaly calculated from 38 observation stations in Indonesia during 15 years, from 2001 to 2015. So we calculate the anomaly precipitation in 38 observation stations in Indonesia from west to east. And the evidence of mixed Rossby-Gravity and inertia gravity in influencing weather condition is not clear due to dominant propagation that takes place over the sea. But I think it is for inertia gravity, because the mixed Rossby-Gravity still have evidence in the Java Island and also Nusa Tenggara. So for mixed Rossby-Gravity wave, it can conclude that still have the impact for about 50%. But for inertia gravity, I think we still not sure about the impact, because the condition is the observation station is not located in the perturbation region.
Do you have any reference about it? Any paper?
Yes, actually it's already published in the paper. I will find the paper maybe.
Okay, yeah.
Yeah.
So we will try to post the paper in the chat after the talk.
Yeah, if
not, then we will send it over the email.
Yeah, because I need to search it first. Yeah, I need to search the paper first. So maybe tomorrow I will share the paper. And then I continue. And for the local condition influenced by mixed Rossby-Gravity multi-level wave to the multi-level wind, we can see here that a lack of low-level westerly wind, there is a less significant connection between local mixed Rossby-Gravity over Indonesia, because we cannot see westerly wind significant in the region of Indonesia, especially in the lower until the middle level of the atmosphere. So we decide that, or we conclude that there are lack of low-level westerly wind and a less significant connection between local MRG over Indonesia. And it is also in line with the paper from Kiladis in 2009. And I think I will close the presentation with a forecast. This is very simple method for forecast, but I hope that it still can useful for you, especially for who want to study about the forecast with a simple method, because we only use a simple method here using the autoregressive method. So we compare the result from autoregressive mode 1 with mode 2 here, and we found that autoregressive mode 2 give a better result than autoregressive method mode 1. So this is the equation for autoregressive here, and this is the flow diagram of how I calculate the forecast. I run the forecast. So we still use a filter wave data using, we divide it into a separate part for model fitting and also for past data, and this is a forecast day. So for model fitting, we use data from January 2006 until December 2015. And for past data, we also use from January 2006 until December 2015, and it goes until December 2018. So we run the forecast within this period from January 2015 until December 2018. So we use schematic, this is a schematic representation of filter 3B42. This is a trim autoregressive process to forecast mixed Rossby-Gravity wave at a certain grid and certain day for 1 to 7 day forecast leads. Like I already described it before, so I don't need to describe it again, I think. And if you want know more in detail about this method, the publication already in the internet, so I think it is also free if I'm not forgotten. So this is the method, and this is the verification. This is the verification result. We calculate the verification by the correlation coefficient here. This is the correlation coefficient, if I'm not forgetting. Yeah, this is the geographical correlation between the filter trim from the autoregressive process to process the forecast against the filter trim observation for mixed Rossby-Gravity wave from day 1 until day 7. So this is a verification result. We use the coefficient correlation here. And we see here that during day 1, the coefficient correlation is higher than in day +2 or lead 7 days. So in here, we also can see that the correlation coefficient is lower in the southern part of Indonesia, like in Bali and Nusa Tenggara here, and it become lower in the day +2, +7. And this is the Taylor diagram to indicating also the verification result here. In the right panel, but in the left panel is for the correlation, still in correlation. for each
I'm
wave.
sorry, on the previous slide, what was the confidence level? Do you remember?
The confidence level. I forgot, sorry, but I can share you again the paper tomorrow.
Okay, no worries.
Yeah, because it's already a long time ago. Yeah. So we go to the next slide?
Yes.
So this is the correlation coefficient for all the wave and also the MGO, because MGO have a long propagation duration, so it should have a higher correlation or higher accuracy. But for mixed Rossby-Gravity, this one, I think, this one, the solid solid gray, we see here that during in day 1 until day 3, we see that the correlation is better than during day 4 until day 7. It go to the zero, almost zero correlation in day 7. It shows us that the uncertainty come bigger in the day plus 7. And this is a Taylor diagram. It also shows us that the correlation is lower and become lesser in the day plus 7. And this is the observation. This is the standard deviation. The standard deviation also become higher. Here the standard deviation, it becomes higher in the day plus 7. And mixed Rossby-Gravity exhibit a constant decrease of the correlation coefficient and a constant increase of sorry, I think it is I put the wrong conclusion, but this is the information about the figure. But from this chart, we can see, or from this graph, we can see that the method still give us a better forecast until day plus 3. And here we have the summary here, the conclusion. From the discussion with the other paper, mixed Rossby-Gravity have a less magnitude, especially in the Indonesian region, and mixed Rossby-Gravity wave confine more to the equator compared with equatorial Rossby, and it's also in line with a paper from Matsuno and also Gill. And the mixed Rossby-Gravity bound over the equator during December, January, February, and spread northward during July, August, and September. It also in line with the paper from Ramage. And for the precipitation, local mixed Rossby-Gravity relationship, especially in Indonesia, with a lesser anomaly rate. So it shows us a lesser anomaly rate. It can compare with other wave also. It have a less relationship to the precipitation anomaly. For the multi-level, it also show that it have a less connection between local condition and mixed Rossby-Gravity wave over Indonesia. And for the conclusions, the influence of mixed Rossby-Gravity in the Indonesian region is not too clear compared to other equatorial wave, especially with equatorial Rossby and also Kelvin. And MRG takes 2 days of propagation to cover the whole Indonesia region. The coordinate is from 95 to 145 east, and takes 2 days to persist in one point or one coordinate or one location in Indonesia. And MRG forecasting using a simple statistical method in this paper is using the autoregressive tool to the filter satellite data is still useful to predict at least up to day 3 forecast lead time. And I think that this is the end of my presentation. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much. We will now welcome any questions. You can post them in the chat. You can also unmute yourself or anyone from here, from the room wants to ask a question. So I've got a quick question, Dr. Ida. Oh yeah, okay. I will just keep my question for myself. There's another question, so can you read the question, or would you like me to read it?
Yeah. Recently, a group of experts from have mentioned about the role of energy in conversion RMGS. Yeah, for mixed Rossby-Gravity wave, like we can see in the previous, we can go to the previous slide here. I hope I answer your question correctly. So from Tatsuka and Sato in 2020, we can see here that the mixed Rossby-Gravity also influenced the modulation of perturbation in the Indian Ocean. I think it also relate to the MCS feature here, but in Indonesia, I think we can go to this one. I think in the practical, Mas Rezza also will give you the example also for the influence of mixed Rossby-Gravity wave in Indonesia, especially for the MCS mesoscale convective system in feature in Indonesia. And we can see here that in Kalimantan, we see that the feature, it's look like the MCS or mesoscale convective system is triggered by the mixed Rossby wave here. It is also the feature here is still coincide with the positive perturbation in the filter mixed Rossby-Gravity wave. So I think, yeah, for Indonesia, it still has a quite good response and quite good connection between the mixed Rossby-Gravity wave with the MCS. I hope I answer your question. Thank you.
Yes, that was a clear explanation. I know Thierry has a question.
Well, it's not a question for Ida. It's a remark for the forecasters. What the forecasters who read this kind of papers, it's just a recommendation, is to recommend you that what could I keep interesting for my regional forecasting, for example, and give me the, okay, I should read this paper in depth and ask questions to Ida later on. It seems that there is something for my region, and I need more time to understand what's behind, etc., what's the processes, so the process of transferring science to operations is on both sides. So the scientist, when writing a paper, maybe should try to understand how useful could it be for the operational, and then the forecaster should ask himself or herself, what can I do with this? Can this result help me to understand in my region? It's a long process. It requires years, but so that's just a remark. The transfer of science to operations is not an easy process. It starts with like extracting the juice from a fruit to make what you need to make better warnings, for example.
So you also you mentioned at the last slide that and previously as well that mixed Rossby-Gravity waves are less known and their influence on rainfall is less studied. I'd like to ask you if through your experience, through your forecasting experience and also scientific, with a scientific background, do you think it is something worth studying or not that much?
Yeah, I think for mixed Rossby-Gravity, as we see here from the slide, from the result of the research, that during the Asian monsoon or during the boreal winter, mixed Rossby-Gravity waves still contribute to the positive anomaly of precipitation in Indonesia. So I think, yeah, because in CICS there still no feature that showing us the mixed Rossby-Gravity wave, because we usually in operational we usually use NCIS, so sometimes we ignore it. But maybe later Mas Rezza will explain how the mixed Rossby-Gravity also give an influence in Indonesia, but compare with other wave like in Kelvin and also equatorial Rossby, it give a lesser influence. Yeah.
Yeah, I agree. Thank you very much.
Welcome.
Another question: how different is the signal from a mixed Rossby-Gravity wave and a TD? Both propagate west.
Yeah, it's quite difficult to answer because I'm not filtering the TD, because I'm using the dispersion from the wave number and wave number and frequency. So I think it's hard to compare with between the mixed Rossby-Gravity and TD in my research. But if in my opinion, in general, MRG and TD, as maybe I'll show you the previous slide. So the MRG still have a strong connection with the tropical depression type. So I think it's still hard to determine or to identify, but yeah, maybe in the other paper we can find the answer. But for me, it's hard to answer because I'm not filtering the TD.
Philippe Berrier, are you here? Philippe?
We just started to ask individual people, so be prepared, whoever is there on the Zoom. So I can add something while we are waiting for Philip, that I would say that in general, mixed Rossby-Gravity wave can be has a lot of in common with a TD, but the TD will eventually strengthen and it will exist at as an independent feature. And a mixed Rossby-Gravity wave propagates and it is never as strong as TD. I think, yeah. So is Philip there?
Waiting for Philippe. TD is a easterly wave, not only African easterly waves, but in Philippe's website, there are also over the Atlantic Ocean and anywhere. They are It's a smaller size. So mixed Rossby-Gravity is supposed to be across the equator. It's a larger size, and TD are even smaller and move faster. So on the website we have two different wave trains: a wave train for MRG and a wave train for easterly wave, and then which may become a tropical depression, but at first it's only easterly waves.
Yes, there's another question, and I think that will be the last one because we are out of time. From the operational perspective, what is the contribution of this product to daily forecasting?
So if you are in the Southwest Indian Ocean, the regional center for the cyclones, La Réunion Island, issues daily ITCZ bulletins in French and in English. So this is for Mauritius, Madagascar, Seychelles, and you can find this on Google, ITCZ bulletin. And my colleagues in La Réunion, they use the equatorial waves very much. And in this daily bulletin, you will read exactly what we are talking about, which means the vorticity or the cross-equatorial flow provided by each of the waves. So this is already in operational at La Réunion Island. And for Western Pacific, these kind of waves are also studied by the forecasters in New Caledonia and French Polynesia. And across Indonesia, as I said, it would be very important to as Ida showed, that the cross-equatorial, the monsoonal flow, cross-equatorial monsoonal flow is strengthened during 1 or 2 days and then is weakened again. And when you have an island which is perpendicular to the flow, then you have more orographic enhancement and coastal convergence when the wind is strong. So as soon as the flow is perpendicular to your island, mountainous island, then it's important to understand that the wind will be stronger or weaker because of 1 or 2 waves.
All right, I think we can close the Q&A and make a little break. Let's meet again maybe 20 past 4, so in 8 minutes. So just to have a practical session and again Q&A. Thank you very much.
Thank you for helping me out. Because to be honest,
ready? Ladies and gentlemen, welcome again to the practical session. Today we will have Dr. Muhammad Rezza from BMKG. He will be talking about mixed Rossby-Gravity waves.
Okay, thank you, Beata. Let me share my screen. Okay, it's okay. I will hold it. Okay. Yes, okay. Thank you. Okay, and maybe before I start, I will sorry. Wait a moment. I will share the link so you guys can download the data. Okay. Okay, so I share in the chat the Google Drive, so you can download the data, and it will take some time because very large of the data, like say about 1 gigabyte, and the inside the folder, so you will have like the data. So this is the OLR data. This is maybe important, so it is first priority. You have to download, and the day for exercise folder is for the source code. I will use Jupyter for in this practical session, and other is maybe this JS map also, and see Himawari data is very large, so this is the last priority. So you can download this. Okay, so let me start. Okay, oh, sorry. Okay, so first of all, let me introduce myself. So I'm Rezza. I'm staff now for Center for Applied Climate Service, BMKG Indonesia. And before I was in the Public Weather Service, same with IDA. And I also partly work as the senior forecaster at that time. So in this practical session, maybe I will talk about from the operational perspective. And from this exercise, so it's very maybe easy to follow. So the target is you can create the homoflow diagram of OLR anomalies, and you try to identify the MRG-like westward propagation before filtering, and also they analyze the MRG filtered result. So as the introduction, so actually, to be honest, the MRG compared to the MJO and the other equatorial waves such as Kelvin and Rossby is not still included in our forecasting procedure. So hopefully through this workshop, we can enhance together our understanding, and as Thierry also said yesterday or the day before, that the object approach of the analysis is very important. So if we are able to detect some objects like MCS or something moving westward or something, so what is happening actually and what is the trigger of that? And for study cases, I will use the October 25, 29 and November 1, November 9 this year, 2023. And what is actually happened is, sorry, maybe this one. So maybe this one is more with animation. Okay. I hope it move. You can see it move. Okay. Can you identify some features like cloud in the Western Pacific area, just in the north part of Papua New Guinea and also Papua of Indonesia over here? So this is the how to say, the animation from 25 October until 29 October. So we'll use this to understand or to see by the practice reading and plot the data. Okay, so first maybe you can, I will stop this and share again my screen. So first is maybe you can, I will show this, sorry, wait a moment, my screen. Okay, so I will try to plot the satellite data, the GSMAP first, okay? So you can open the GSMAP case of Jupiter, and the code is like this. So first, the data itself is consists of several net CDF for each hour of data. You can see the inside. So this is the case 1 is for the October case, and case 2 is for the November case. So when you have the single net CDF, what you have to do when you want to plot the half molar is just collect this into one folder, so you can read one at once. So like this, so just input the module like this and run this cell. And after that, you don't need to change this, because maybe it will read automatically the folder NCGS map where you put the NC. So because we just put into the single folder in the case 1, so it will read all, something like this. Okay, it takes a moment to read. So now if you want to know the okay. Like this, so you can check the variable by using this. This variable, so it will show the variable. There is latitude variable, longitude, and from because the GS map data is from north 60 to the south 60, and this is the time. So the time will automatically read by the package. So I put the time for October 25 until October 29, like this. So when you have several this time series of data, and then there is also a variable, the important variable that we want to see. So GSMAP is the rainfall product provided by JAXA, agency from Japan. So this is the rain rate variable. So we can check this. For instance, we want to know the shape of the rain rate array. So like this, we can just run this, and it will display. And now we want to make a half-molar diagram. So when you want to make the half-molar diagram, you have to define the latitudinal band you want to analyze. So for instance, if we want to analyze, for instance, the maritime continent region or Indonesia, so it is like between 10 minus 10 or 10 south until the 10 north, and this is I said Indonesian region, but actually GSMAP data cover all globe from 0 degree to the 360 degree. So for instance, I will crop and for the maritime continent region between 90 to 150. And with this, so we can crop the large global data set and how to say 120 times a slide into this small area, and we can just plot like this. And for instance, we can run this and we can see okay, sorry, I didn't run this. Okay, I will run this and then run this. Okay, wait a moment. Okay, so the result is like this. So what happened between the October 25 to 29? So you can see this is the half molar you create, and this is for the y-axis is the time, and this is the longitudinal from the 90 degrees east to the 150 degrees. So Indonesia is about in this until 140, yeah, until this. So this is the rain rate. So highest rain rate indicated by the yellow color. So you can see here. So about from 2006, from October 26 to 28. And you can see that this is, the time is from below to up, right? So we can reverse it to easy to understand. So which one with signature propagate westward or eastward. So you can just put this. So this is will invert the x-axis, the y-axis, sorry. So we can see, so can you see the signal, the westward propagating signal, and when it happened? So yeah, around this this part, okay? So maybe I will draw, okay. So like this. So you remember the animation, the satellite animation I showed before? So like, because this 140 is the longitude for Papua area. So it is, it show the cloud cluster which in each day moving to the west. Okay, so and then how to erase by the way? No, to erase the annotation. Yes. So next, maybe. Okay. 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 So now you can easy make your own half-mole diagram using GS map data. You can select your each region. You can make it smaller, or even you can make a shorter latitude band. For example, if you have just want to from the -5 to 5 like this, it's okay. You can also make like this. And then finally, and then after that, actually, so when you want to filter some wave, so for example, Rossby wave or Kelvin wave, so which is the maximum or the limitation of the frequency resolution? So it will depend on your data time resolution. So for instance, if you have hourly data, so the maximum frequency that you can get is double of it, so about 2 hours. So if you have daily data, the smallest frequency you will have is the 2 days period of the wave. So if you want to, for instance, you want to filter the more high frequency wave, for instance, the inertia gravity wave, I will back to this slide. So you can see more the right hand axis, the vertical axis is the period. So this is 2 days, mean 2 days. And so for example, this one is, I think you can see my cursor, right? Okay, so this one is for inertia gravity wave, and this one is for, this is also inertia gravity. So this is the short period of the wave. So MRG is usually like from this curve. So what Ida have shown that in Indonesia, the low zonal wave number mean like twice cycle around the globe, or like can cover whole Indonesia, is actually in this area, in this part. So with zonal wave number 1 or 2, and with the period above 3 to 2 days. So you have to at least have daily data to catch this signal if you want to filter. And then what important thing that you need also to calculate the anomalies. Why we need to calculate the anomalies? Because for instance, like temperature, here is shown the rain rate is, we need to explore the wave characteristics. So if the change like this, for example, this one is, we need to find the positive or minus change. So for example, if this is the minimum is, for example, maybe 2 millimeter or 1 millimeter, for instance, and the highest is maybe 10, for example. So yeah, we can also, I mean, we can say this is such a wave, but we need to find the plus and minus. So that's why we need to find several reference, and usually from the mean. And so this one is become plus, and this one is become minus. So this is already met the characteristic of the wave, so we can do some filtering. So for that, we calculate the anomalies. One method is you can just subtract from the mean or the climatological value. For easy, I just calculate the mean here. Yeah, this is, I made mistake, should be mean, and yeah, and this one also mean. So this one is, I calculate just mean of the whole period and area in this figure. So just run this, and we can see this is the mean is 0.2 millimeter per hour, because the data is hourly data. And then after that, I will try to put some. Yeah, and because this is the rand rate, so if you need to exclude the zero, so let's do this, and sorry, this I should change to mean just to. So we will exclude, we will take only positive value, so zero is will be neglected. So you can see the difference, right? So the mean is very low at the first, because we calculate, we include the zero value, and when we exclude the zero value, the mean is like 1.9 millimeter per hour. So now maybe it's supposed to be okay. And here we calculate the anomalies. So anomalies just simply subtract your data with the mean value, either the climatological value or the mean value for whole your analysis. So you will get plus minus to match the characteristic of the wave. And then here we go. So you can see, okay. Yeah, so this one is now, can you still find some westward propagating feature? Yeah, positive value mean more rand rate, right? And negative value mean less rand rate, the red one. The blue one is the positive value. So you can find the westward propagating signal over here, okay? Yeah, so that's, and then after this, after you made an anomalies array, you are ready to the filtering to the filtering to the wave what you want to filter. For example, Kelvin, MRG, or Rossby. And yeah, if you have any question, you can just ask. And
just a little remark, because the wave, like you said, Kelvin, MRG, and Rossby, they would look different on a Hofmüller diagram because of the direction of propagation.
yes.
Yes, just to clarify this.
Oh, yes, okay. And then let me, and then after, this is the example cases of one case study, so very short time period. Next exercise would be, we try to read the climatology of the OLR. OLR is, how to say, very common to use, because it is global data, and can be also used as the proxy for the rainfall, because it can represent the convection. So we actually, for the, maybe, yeah, for operational basis, we usually use this website from the NCICS. And for the filtering code, maybe yesterday or 2 days ago, it's already explained, right? You can download here. It is available here for the filtering, and Derek also explained yesterday, I guess, the procedure to set the wave number and frequency when you want to conduct the filtering. So it is very similar to this. So for MRG itself, is in this method, in this algorithm, use only filtering the wave number and frequency. So like the purple box here, over here. So you just select which minimum frequency, maximum frequency, and also zonal wave number, maximum zonal wave number and minimum zonal wave number. So something like that. But for example, equatorial Rossby or Kelvin, they use the theoretical shallow water equation for the Kelvin. It is also you can search and calculate it using the such kind of formula. And also MRG, if you want to specific filter the MRG, you can add this line. I think you can see my cursor. This line. So this is the theoretical of MRG of shallow water equation solution. And because this for in this NCICS, the method is they also want to filter the MRG TD, so they use this box filtering, fall filtering. Okay, so in this sorry. Oh, sorry. Let's move back. Yeah, so we can also find Hofmuller like this for several parameters, but in this practice we will just use this OLR, and but unfortunately for in this default Hofmuller product, no MRG, so we need to plot by ourselves. Okay. So we will exercise of that. So this in this there is Kelvin, ER, MJO, and low frequency, but no MRG. So we need to exercise by ourselves right now. Okay, and then so first let's use this OLR climb. So this is the newest, I mean the updated one for the climatology for the OLR use in this website. We will use the same of this. So this is I convert it to the net CDF, so it really easy to read by using just the simple module in Python. For instance, like this, we just run this, and then we just open this data. So because this is the climatology data, and we want to see the shape of the OLR itself. So there is three variables: the longitude, latitude, and also day of year, because this is the climatology. So this 36 to 6. So this is just want to exercise if we want to see this shape, and if you want to mean, so if you want to calculate the average in longitude and latitude and plot it. And so this will be one dimension of the time and the OLR. So like global OLR peak is around this June, July, August, something like that. Because yeah, you know the reason why the plot is like this, right? And other we want to see something like this. So this is like you want to select which latitude pixel and also longitude pixel. You just enter the number, and it will search the nearest point to this point and then plot. So this is also one point of the time series of the climatology from January to December. And then finally, this one is to crop like before, same similar procedure. You can select which area, minimum latitude, maximum latitude, minimum longitude, and maximum longitude. So then you can run this, and you got the data. And you can also mean whole year. For instance, and you say this. Because I crop Indonesia region, maritime continent, so you can see some mark of island of this graph. Yeah, this is Sumatra, Kalimantan, Sulawesi, and Papua here. Okay, so this is the OLR. And then if you want to make the latitude or the half-molar diagram, so we need to mean the latitude. So remember, our data is between 10 south to the 10 north. So when we average this, it will be between 10, and the result is supposed to be like this. So this is the climatology value. So maybe this is not so clear propagation of the signal because of the climatology. So now let's move on to the, sorry, maybe, yeah. So next, maybe let's move on the OLR data, OLR anomaly data. So once we have the OLR raw data and subtract with the climatology of this data, so we have a time series of OLR data. So this is every day updated. So I got this last run is 15. So like about a week ago. So so the update is just until November 13. So every day this set of the data of this OLR anomaly data is updated. And then subtract with the climatology, and we got this OLR anomaly. So this is similar procedure, just add this module and then try to read the data. And this one is already for certain period, so you don't need to collect each data set one by one. And you can see here, for example, we can select maybe 2003 and 2003. This is maybe until November 10, yeah, for sun. And then this is for the time, and then we select latitude from 10 south to the 10 north, and this is, let's select the globe, 0 and 360 like this. And then we crop the data based on our selection, and we want to see the shape of the data. Okay, so here is the output. And then run the next. And the last is we try to plot the Hofmuller diagram. Okay, so now I plot this with the map, so you can see the location of the maritime continent. And let's see. Okay, so do you remember which month we analyzed before using GS map? October 25, right? Okay, so let's try to make it larger. I mean, let's select that period and see what OLR show us. Here, okay. So let's select this one. For example, from October 1 until November. Let's run this, and run this. Okay. Okay, so let's see. Oh, actually, October here, right? So here, let me annotate this. Is actually there is also, because Here is actually the location of the maritime continent over here. We can check this one. Here is like Western Pacific, just above the Papua. Okay, so this can be a remarkable cloud cluster propagating westward about 3 or 4 days, I guess, yeah. And wait a moment, I will clear this, okay. Okay, so after this, after you prepare the anomalies like this, you do the filtering, and let's move on to the filter itself. Next exercise is to try to see, because we see at the harmful diagram, we don't do any filtering, right? But we see the propagating, the westward propagating signal of the rainfall in the gas map and in the OLR. So what actually that? Let's see the filtering result. So I skipped the filtering running because you can just run according to the yesterday training content. So I just use the filtered one to save the time. So this one is the result of the MRG. So let's try to run this. So we run this OLR wave cfs.nc in the dataset, which you can download. And we run this, and then we try to select the time. Just to click, let's plot from October, okay? Or you can select, yeah, which period you want. Let's select this one. And then you can see like this. So the time is still from bottom to up. So let's invert it using TLTGCA. Invert y-axis. Okay. Okay. So sorry, not inverted yet. Okay, here we go. So now is the top is October 1st. So going to the left would be the westward propagating signal. So we see a lot of westward propagating signal right here. And what we want to see is actually the strong, I don't know, here, right? Around here, there is some, sorry. This, I forgot which longitude area we plot. Okay, from 0 to 300. So Indonesia is between 90 to 150 around this, okay? So the Papua New Guinea is like over here, over this area. And we see this one maybe, sorry, I mistake. Okay. I guess here is correspond to the MRG wave. Sorry. Over here. Okay. So this maybe we can do further analysis about what this is, what relationship and what kind of this coincidence between MRG wave and the cloud cluster, and also with the cloud cluster signal or the MCS over the Western Pacific, just to the north of the Papua. Okay, so maybe oh, sorry, I will erase this. Okay. And maybe this exercise, okay. Okay, it's just Okay, so maybe for MRG filtering plot is until like this, and um, next I will introduce the plotting together with other wave. So why this is important? Because in the wave analysis, the important thing to do is the scale interaction. So the higher frequency wave is sometimes modulated by the lower frequency wave. For instance, MJO will modulate the Kelvin wave, etc., etc. And so when I do some analysis during my on duty as the forecaster, usually sometimes I see the large eastward propagating wave like this, and I also see the faster, how to say, faster, sorry, it's opposite. But yeah, another small scale moving eastward, and inside this, like I see a small cluster of the cloud moving to the west, something like that. So such kind of scale interaction is very important, something like that. So it is also we can try to plot together other wave, for instance, because MRG and Rossby is how to say, the more important feature is the vorticity. So the different one with the Rossby wave is the symmetry between the equator. So we always we often find the twin vortex, something like that, like have shown by Thierry in the briefing today. So like that, and for MRG is the asymmetry. So only one low area, circulation low area, and in the southern hemisphere no exists. So something like that. So that's that important feature we need also to analyze. Sorry, let me erase this one. So we still use the same dataset, the filtered dataset, because this filtered dataset is already filtered all waves: Kelvin, Rossby, MRGTD, and MJO. So we can just use the same dataset to plot two waves. We run this, and then we read the data, and we check the dimension to make sure that OLR, MJO, Kelvin, ER, low, and MRGTD exist. So this is the name of variable. So you just put here to just pick up that value and to set the time, set the latitude band and longitude band. You can set your area over here. So let's run this, and we can see this is the filtered one of the MRG. And we set also this ER. ER is equatorial Rossby, together like this. And we finally, maybe we can try to calculate the standard deviation to see what the difference between the activity of the MRG during the wet pass of Rossby and the dry pass of Rossby. So as I mentioned before about the modulation of the high frequency by the lower frequency, we can divide into wet pass or dry pass, like maybe conducted research by Ida, she focused to the active pass, or we can say the wet pass. So wet pass means because we filter the OLR, the small values become wet pass, right? And the positive values become the dry pass. So let's, for example, it is easy to calculate. like this, for example, MRG, we will calculate the MRG and how to say, and calculate the standard deviation, and then for the whole region, and also equatorial Rossby. Okay. Oh, sorry. Oh, this is the same. I mean, you can try this. Okay. So from this, in this figure, STD is the standard deviation or the sigma. So it is show the variance, right? How active, how change of the MRG become positive, negative, how much change. So we can check the MRG activity during the RB minus 10. So minus 10 is the how to say, the contour of the Rossby wave. So negative is for the wet pass. So how to select this value as in the presentation, it is used like 1 sigma or 2 sigma of the signal. So here in this exercise, I show you this example. You calculate the standard deviation of Rossby is about 7. So you can choose 10 is the threshold to divide active pass and wet pass. Minus 10 is for the Rossby active pass or wet pass, and positive 10 is for the dry pass or the inactive pass. So we calculate the sigma for MRG during the Rossby at this threshold. And then, sorry. Oh yeah, we don't need this. Okay. So we can see that the MRG sigma during ER wet pass is 7.8, and this one is for the dry pass. Oh, sorry, this is supposed to be dry pass. Okay. Okay. So do you see some difference? So sigma is more active. Yeah, I didn't do a significant test for this, statistical test for this. It is different, is significance or not, in which level, confidence level. But because it is just for easy to exercise. But what I did for my master thesis is to calculate this variance during different tests is different. Like during wet pass, the higher frequency of the wave is more active rather than the dry pass. So which means that the Rossby actually somehow modulate the activity of the MRG. So when we see the Rossby wave and MRG wave together, it's something like it would be modulation or or we can say more cloud cluster will happen and we're strong, something like that during that. This is one easy example to analyze, something like that, that we can see the difference between the activity of the MRG during wet pass and dry pass. Of course, if you want to further doing some research, you have to do statistical tests or significant tests to see this such kind of difference is significant in a certain level. Yeah, so that's maybe maybe my time is over, right? Okay, so yeah, this is maybe at the end of this my exercise, and I just want to close my session that MRG and equatorial Rossby is similar. They play important role by the vorticity. So by looking at the streamline, like what actually already forecasters do, and like this is this pressing drawn by the forecaster each day. They draw the circulation and how yeah, actually this study case is actually the circulation is right here, right, but it is cut because not in this region, but actually you draw some signal maybe correspond to the MRG and Rossby wave. And yeah, Also streamline the forecaster on duty. Also, I confirmed this to the Vivi this morning. So this actually should be cyclonic, right? Cyclonic circulation, because counterclockwise, so the level, and next day it become the low, actually, like this. And yeah, and it how to say become, and also exists until 2 days later. So this is how MRG somehow, if there is circulation, so some signal or some clue the existence of the MRG, and even because this is how to say, or if there is like kind of twin factor, twin vortex, it might be equator Rossby or something like that. Yeah. So, and it associate with the cloud cluster mesoscale convective system over Western Pacific. Yeah, that's maybe my presentation. Thank you. I return back to Beata.
Thank you very much. It was, I think it was really great to listen to someone who is both a scientist and a forecaster. So we had an insight from both worlds. So we've seen a lot of Hofmüllers, and they were based on rainfall, OLAR, and there's a question in the chat. So what makes such a difference if we considered brightness temperature rather than OLR or rainfall?
Okay. So brightness temperature is actually how satellite measure the, yeah, it is called brightness temperature because it is like how satellite measure the top of objects. So if there is no cloud, of course the top of the object would be like sea surface or land surface, but if there is cloud, it would be the top cloud of temperature. So OLR itself is the outgoing long wave radiation from the Earth. The unit is the watt per meter square, and the brightness temperature is in the temperature unit, Kelvin or degree Celsius. But actually this temperature also derived from the radians or the OLR. So from watt meter per square, we convert using the Planck equations. So yeah, you can search, you can Googling of that equation, can convert to the brightness temperature. So it is like similar, but like different units, something like that. Yeah.
And another question, where did you get the filtered OLR netcdf file from?
Okay, so as I showed before, we got from the, I think my, oh, sorry, this one. Yeah, you can visit the NCHS and, oh, sorry. Yeah, you can visit the NCHS website. Okay. And there is some code, and in that code there is some tutorial, the source of the data. This is CFS model data and also CDAS model data when we can download, so we can get access to obtain the raw data. And you need to run the filtering, so you can you get the raw data from that source of the model data, and you subtract with the anomaly data, the climatology data, so you get the anomaly data of OLR, and you filter, just run the filter, and then so you can get the filter. So it can be used for operational purpose. Yeah. And yes, something like that.
Yes, this is Thierry. We have a message from Philippe Perrier about the question about the difference between easterly waves and MRG. So I read, So the MRJ have a strong equatorial waveguide, a large possibility of wave numbers, and an analytical solution. The easterly wave, TD, is not only a tropical depression, it's easterly waves. They have no analytical solution. There is no waveguide, and there are more wave numbers. It's more synoptic. So in general, the signal is and period is similar, but MRJ is more centered over the equator. That's the answer from you.
Thank you, Philippe. Do we have more questions? Yes. There's a question. And
may I show my screen? Just a moment. Sorry, here maybe I will show the data source. Like if you open the NCHS website, so there is information about the data. So this like CDR model and for the OLR data and something like that. So you can refer to this website to obtain such kind of data. Yeah, this is just additional information. Thank you, Beata.
so the next question is, does the forecast visualization site incorporate vortex removal in forecast mode? Can you see the question? I think the person is referring to the same site.
Sorry, I don't understand. The forecast visualization mean?
The forecast visualization site, I think, is the site which we've just seen on your screen.
Ah, the website? Ah, okay. Okay.
I don't entirely get the question, honestly.
Yeah, me too. I mean I don't.
Can you maybe
Can
clarify?
You yes. Oh, sorry, I cannot see. I need to stop share first. Ah, this one. This one. Sorry, I don't understand.
Sorry, can you maybe Misva? Yes.
Maybe Thierry can answer.
MISVA site, the vortex removal in forecast mode. I don't think so. We'll ask Philippe, but I don't think so.
More questions? We are slowly approaching the end of the session.
I have a remark. A few years ago, several years ago, there was a website available with the Hofmodel for rain. It was Michael Ventris, and I liked it very much. It was great to see the rain, which is the real weather. and then Mike Ventris had a problem, I think, and then now we don't have any more in operational mode. So the scientists they get it for the case studies. So why can't we have? Is it difficult to have this on? So it was the past and then the prediction in GFS. So could the forecaster get this?
Yeah, actually, for the half, usually we why we first use the Hofmodel diagram because of the before maybe by that and NCHS is from 2019, right? We use or 2018 something. Yeah, before that we only can just rely on the Hofmodel because the tapering case, right? We cannot after filtering or after filtering there is on always gap for the end of the data. So when we see the Hofmuller diagram, we just see the propagation of the MJO at the time, the main trigger for analysis in making weather prediction. So until how to say, if we do filtering, there is also always cut at the end of the time series, right? Because of due to the tapering. But when the NCHS provide the continue from that tapering, so the data can exist. So we use that for that. We are become able to see the forecast continue, like from the Hofmuller diagram, something.
Yeah, there are two products. Well, the observation would be still very interesting, and then forecast is something else. Yeah, plus, but yeah.
Before we very difficult to how to analyze or how to analyze the forecast until the end of the time of for example the time longitude data is until today, but due to the filtering like 3 days just before today is already cut, right? So it is very difficult to see the forecast of something like MG or something. But yeah, when there is a forecast, the Hofmuller together with the forecast at the end of the end date of the time data, it is very useful. So that's why in the operational basis we use such kind of product, raw data together with the forecast data in Hofmuller. Yeah, thank you. But that is very nice information for the rain, right? Yeah, we need to consider about that. And how about how do you think about the MRG? Do you think we need to put it in our prediction procedure? Because now is we just rely on the MJO, Kelvin, and Rossby.
Yeah. Well, especially because we don't have the rain, we are not used to follow the rain or even the OLR. We don't follow the OLR very much. We use the ingredients. So the wind, we don't have the convergence. We only have the wind, wind field, and the moisture. So for tropical cyclogenesis, we look for vorticity very much. So my colleague in La Réunion, they really follow the moisture and the vorticity through the wind and through the stream function. But we don't follow so much the rain because we don't have the tools only, maybe. So if we want to predict the extreme of rain, we would need maybe some Hofmuller of rain.
But I think that could be one of recommendations for the future. There's another question, and I think it is to Dr. Rezza again. What is what is all expert opinion on detection of tropical waves based on machine learning, post-processing on real time?
Ida, you can answer about this. Yeah, I will let Ida to answer first because she experienced in how to say conducting forecasting using the statistical approach. So maybe rather than doing such kind of complicated filtering, so Ida, maybe you use statistical method to forecast the MRG. Maybe you have kind of point of view. For me, you can answer first.
Sorry, but for me, I haven't read a paper before about machine learning used for identification of the tropical wave. But I think for me, it is the time filtering, space-time filtering is still a good methodology to identifying the equatorial wave because it's following the shallow water equation, and I think because it's remove the background, so it is also still reliable in this current condition. But I don't know, maybe other experts have a understanding more about this.
I think it can be difficult, but I hope it's possible. The difficulty can come from the fact that the waves are already the anomalies. So it is hard to predict the rainfall, like the, um, the total. And if we just focus on the tropical waves, it is, I think, even more difficult. And also there are many interactions, but I have no experience. Like I just, yeah, I mean, I have some in machine learning, but not regarding tropical waves that much.
And in my opinion, I think if we want to detect the cloud cluster which moving eastward or westward, perhaps maybe it is possible to conduct the AI, but to distinguish, yeah, even with the filtering, it is difficult to distinguish this one is MRG and this one is MJ or something like that is maybe, yeah, hard enough, I think, if using AI or machine learning, I guess. Yeah.
Maybe the pattern recognition could help.
Yeah,
I don't know.
for simple propagation maybe, yeah, but for wave to identify the wave is without filtering is, I think, very difficult. Yeah, we need to conduct filtering.
But that's for sure an interesting topic, and
Yeah,
it will
I
probably
agree.
grow in the future.
Yes, I agree.
Okay, there's another question about a specific place. Maybe Thierry can answer this.
Daira, what it is, Daira?
Yeah. It's a province of
Yeah.
Where?
Indonesia.
No, it is general term for the province. So BMKG is the headquarters. So BMKG has several kind of branch office. So it is like office in the province level or
Yes, but
district level.
is it a geographical question or is it, no? No, it's not about regional forecasting or no? It's
Yeah,
no, it's a general question. Okay.
Yeah.
I thought it was okay. What is the reason for well, it's a bit the same answer for the artificial intelligence. Is that my view is that a forecast, as I said, as Philippe also said, Philippe Perrier, if we want to work as a human forecaster, we relate on objects, the object approach. So we recognize some ingredients. So what's interesting, for example, for me in a Kelvin wave, it's not that it's a Kelvin wave, it's that it's a westerly wind surge. So again, if I am in a region which is sensitive to westerly wind burst, then it will alert me about and I can follow this object which moves eastward and which will reach my region in 3 days, for example. It's easier to have isolated the object of Kelvin wave to make the movie of the scenario of the possible extreme rain in 3 days, Than if I only look at the rain from the model. Even if the model is good, I will be more alerted about, and so that's why. So I need the ingredients. I need to understand, for example, the MRG. Okay, we know the reservoir model, but I need to understand what makes the rain. So if I am to be here in a forecasting room, I need to understand the process between MRG and the rain in my city. If we put AI, then I can go home. Thank you.
All right, let's go home because the time is up. So I hope tomorrow we will also have some questions and insights from different people. We start 2:15, and tomorrow's topic is the interaction of waves with cold surges. So it's gonna be a bit different than today and the last days. So I hope to see you tomorrow, and thank you very much. Thank you to the speakers, and thank you for attending.